Okay, time to get started. Real quick before we get into the math, don't forget to do the attendance quiz. Number on the board over there. Another quick reminder. I cannot be relied upon to always remind you to do the attendance quiz. Again, just a reminder that's going to be a student responsibility thing. So make sure to have some sort of procedures in place where you can reliably remember to do it yourself. Okay, all right, back into the math. So, we were doing this example last time. This is an example of using the multivariable chain rule. Quick reminder where that came from. The multivariable chain rule comes from thinking about how when you compose multivariable functions, and with the understanding that the derivative turns input changes into output changes, more specifically that the derivative is a factor that accomplishes this goal. Really, this is just the observation that the total factor is the product of the individual factors, right? And again, it's a pretty believable point of view, I think. So we were back to our example here, and what we did is we applied that last time and computed the derivative matrix for the composition as this. Okay, that was the first part of the question. The first part of the question was to compute that derivative matrix. Second part of the question was to compute this specific partial derivative. And notice this is specifically the partial derivative of Z3. Now let's take a quick moment. Where is Z3? Here it is. There's Z3. It's the third output of the composition. Right. And we're supposed to compute its partial with respect to x1. Where's x1 in this picture? Well, there it is. It's the first input into the composition. Okay, so how are we going to compute that partial? Well, we just got through computing a derivative matrix that's made up out of all of the partials. The one we are interested in being one of those. Right? So we just have to identify which one of the 6 partials that we just computed is actually the one that we want. And all we have to do is remember what the structure of the derivative matrix is. Specifically, output variables correspond to rows. Right? If we're looking at the third output, we need to look in the third row of our derivative matrix. And furthermore, input variables correspond to columns. So let's see here. We're looking at the partial with respect to the first input variable. Therefore, we're interested in the first column. So we're looking for that specifically, that partial derivative of the matrix we just computed. And so, boom, answer is 3. All right, how we doing? Is everybody on board? Don't forget about the attendance quiz. By the way, I hope it's... anyway, I gave you one reminder. I hope everybody got it. Okay, so, so moving along. Let's see here. A couple of special cases to talk about. Now, these special cases are pretty common. Comes up a fair amount. And I think these being special cases simply being a matter of just plugging in certain values for the dimensions of the spaces in question. It's a pretty straight read. You are going to notice this is listed as for students to read. As usual, I am going to hit some highlights. So looking at this first special case, we're considering here what happens when there is only one original input variable. That's an input to the first function in the composition. What does that do? Well, what that does, among other things, is it means that this first function has only one input variable. That means we're looking at position in Rn as a function of one variable, which, again, regularly we like to think of as being time. And position as a function of times means you have a parametric curve, and that means that its derivative matrix, which, of course, one input variable means one column, its derivative matrix is the velocity of that parametric curve. All right, now that's one of the consequences of the fact that we're looking at a special case where there's just the one input variable. So next observation, The composition also is a parametric curve because that composition is now position in Rm as a function of, again, time, right? And position as a function of time means it's a curve. Again, we have just the one input variable, therefore just the one column. And the derivative matrix of a parametric curve is, again, the velocity. So what we have here, what the chain rule effectively states in this special case, again, the special case being one original input variable, the punchline is it's basically just telling us that when you have a function, a multivariable function from Rn to Rm, the derivative matrix is the thing that you multiply by input velocity to get output velocity. And again, that's something we already knew, right? So this is not telling us a new interpretation, really, of anything. I guess you could make the case that this is a new interpretation of the chain rule, right? But it's an interpretation we already knew as one of our primary interpretations of the derivative matrix. That's what derivative matrices do. They turn input velocities into output velocities, right? So anyway, heads up, you will actually see this sometimes. Sometimes when this gets written down, it's written down and stated as a property of the derivative matrix, and other times people will refer to this as, hey, here's the chain rule. And they're both right. Okay. All right, so example below, again, pretty straight read. Again, hitting the highlights, and input velocity is given. The question is to compute the corresponding output velocity, and the thing that you multiply by input velocity to get output velocity is the derivative matrix. So you compute the appropriate partials, you plug in at the appropriate point, blah, blah, blah. Y'all can read the details. That's all that is. Okay, now a special case of the special case. We've already considered what happens when you have just the one original input variable that makes these velocities, right? This is an input velocity, this is an output velocity. But now we're going to consider the additional special case. Let's see if red is contrasting enough. Where there's only one output, eventual output variable. What does that do? Okay, well, let's see here. That means that there's only one output from the composition. Let's see here. What the composition has only one output. Right? And if the composition has only one output, wait a minute, it also has only one input. That means the derivative is just a single variable Calc 1 style derivative of one output with respect to one input. It's Calc 1, right? Okay. The other thing to notice is now this function here, what you might call the second function, the function in whose domain and target we're looking at sort of two parametric curves. That has only one output. And again, outputs tell you how many rows you have. So one output means one row in this derivative matrix. So what that does is it changes things just a little bit, or it allows you to change things a little bit because this derivative matrix is a single row. As we've previously observed, you can kind of reinterpret that as dot product with the gradient vector. So a different take. So instead of viewing the chain rule as a statement about features of the derivative matrix, in this special case of the special case, you can interpret it as giving you an interpretation of gradient vectors, which again, kind of the same thing. Okay, so again, special case, input velocity, output velocity, dimensions tailored, appropriate to this, that this is an example of. I think this is, again, a straight read. Give it a look. Something y'all can do on your own. Okay, new point of view. Let me start by reminding you, as we've already discussed, but worth saying again, what we have done so far is we have viewed the chain rule as being a statement about matrices, right? Because a matrix times another matrix gives you a product of those two matrices, right? I mean, it's, old observation. Okay. All right. Fine. But sometimes we actually don't have a specific interest in the entire derivative matrix. Sometimes you don't need to know that. Sometimes, fairly often actually, all you really want to know is one particular partial derivative. Right? So notice we've got a composition of functions here, right? F turns x's into y's, g turns y's into z's. Right? We write down those derivative matrices here and here. Again, be careful about the order. Don't accidentally switcheroo. Right? That's a real problem. It leads to a lot of wrong answers. There's our chain rule as we currently understand it. But if all you care about is that one partial derivative, I don't need to know any of this stuff. Then I'm not going to need to know any of that, and I'm not going to need to know any of that, and I'm not going to need to know any of this. And, my gosh, there's a lot of stuff in this full matrix form of the chain rule that we don't need. Right? If our interest is that one composed partial derivative. So, this new form of the chain rule I'm going to give you all is just the observation that when you want to compute an element in a, wrong tool. If you want to compute an element in a certain row of a product matrix, you only need to know that row of the left matrix. And if it's in a particular specific column, you only need to know that column of the right matrix. Matrix multiplication, right? And then you can just kind of follow the usual rules. That particular element's computed as a dot product of the green coordinates dot the blue, right? I mean, that's just dot product. And so, nice little punchline. What we have here all together is a new coordinate form of the multivariable chain. Right? It's just matrix multiplication. And again, if this is all you care about, then it leads you to realizing the sort of bare minimum number of partials that you need to compute and exactly what to do with them. Okay, nice in a lot of instances. Now, this does come with some warnings. So, it's easy to mess this up. It's really easy. I've seen this a bunch of times. Lots and lots of times students step on the following little landmine where they think to themselves, they start writing down this formula and they get down to here and they think, hey, wait a minute, hold up. Don't these just cancel, thus leaving that to be that and this to be this? Aren't I done here? Right? Why don't I just stop at that point in writing down I feel like we're done here, right? And students will stop right there and not write down the rest of the formula that we have just established, right? So, what's wrong? What's going on there, right? This is a little concerning. Well, aside from the fact that it's not the formula that we just wrote down, right? I want y'all to understand not just that there's a problem with the claim, but there's a problem with the reasoning. It's subtle, but dangerous, right? There is a problem with that reasoning, and that problem is that these do not cancel. You cannot cancel them. Because those two things aren't the same thing. And this is a really unfortunate feature of partial derivative notation. This looks like a thing. That's the denominator of a fraction. And if this is in fact a thing, you would think that the notation would be specific enough that that thing is the only thing that's being referred to by that notation. And I'm sorry, I wish it were different, but that's just not true. Right? That and this are different. Oh gosh, what a really unfortunate piece of notation. Why do we write it like this? And the short answer is that any notation that would fix this problem is quite a bit bulkier and more inconvenient to work with, and the mathematical community just doesn't want to. Basically, is the short answer. So what that means is, yes, we're going to stick with the relatively efficient notation that we have, but it comes with this warning of you have to interpret it carefully and not make these assumptions. So let me try to persuade you that these are different things. These two different things are part of two different stories, basically, is the point here. And let's think about on the left-hand side, what's the story? What's happening in there? Well, in this computation, we are making certain assumptions. Taking a partial derivative, partial with respect to y1. When you take a partial derivative, you hold all the other input variables constant. That means that y1 is the only one of the y variables that's allowed to change. All of the other y variables are constant. That's how partial derivatives work. Okay. What about this story over here? Right, looking at the right factor. What's going on in that story? Well, okay, we're taking a partial with respect to xj. That means xj is the only x variable that's allowed to change. We're going to hold all the other x variables constant, fine, but are we holding the y variables constant? No, that's not how partial derivatives work. And in fact, because we're changing an x, and because all of the y's are functions of all of the x's, when we're changing xj, it kind of follows that all the y's kind of have to be changing. Right? So not constant there. Right? So these two things that we have labeled as partial y1 can't be the same. They're part of different stories. It's like a silly metaphor I like. If you're reading two books, both books written by different authors, happen to have a character named Steve, yeah, they're not the same guy. Right? Same name, totally different scenarios, they're not the same people. So same things going on here. So these are different. You cannot cancel them. And independent of the fact that this gives you a wrong answer, even worse, it's not valid reasoning. All right, does everybody see the point there? Okay, so do not, please, do not step on this landmine. Do not write this down and declare yourself done. It's nonsense. Absolute nonsense. Okay. All right. So let me give you a different way to think of this equation. This is just a recopy, so I can have it on the screen conveniently. Same equation from the previous page. Different way to think about it. I think this is really useful. Really useful. It's an alternative point of view, but it's a fabulously convenient point of view. So here we go. We're again thinking about how Zi changes as a result of changing xj. This being a partial derivative, of course, we are holding all of the other x variables constant. All of those are held fixed. And let's just think now about what happens as a result of making little changes to xj. Right? So imagine we just sort of, are jiggling xj just a little bit. What happens? Well, when you change xj, among several other things that's going to happen, changes in xj will cause changes in y1. Whatever change it is that we do to xj, that what I have in orange represents the factor by which that change is magnified to get the resulting change in y1. And check it out. That factor is this partial derivative, that is that part of the equation that we're looking at. Okay, fine. So what? Okay, so y1 changes, big deal. Well, here's the thing. As y1 changes, sure, there's a bunch of other stuff going on, and y2 and y3 are changing as well, but let's ignore that for the moment. Just exclusively because of y1 changing, that contributes to a change in zi. And now you'll notice that factor right there. So, okay, well, altogether then, moving along this path, ignoring the other paths along which changes can propagate, whatever change we make to xj, the product of those two factors, the orange times the red, is the factor by which changes in xj contribute to changes in zi, and that product is this term. Okay, so nice little convenient punchline then. Paths along which changes can propagate contribute terms in our chain rule. And et cetera, for other paths, you get other terms. And so, yada, yada, yada. Here's another path by way of the intermediate variable ym. That gives this term. And likewise for all the terms in between. All right, so the big idea, terms in the chain rule. Let's see here. Terms in the chain rule correspond to paths in the diagram between the variables in question. And then, by the way, let me also just kind of notice every one of these paths, you'll note, corresponds perfectly with one of these variables, one of the variables in the middle that we call intermediate variables. So, excuse me, so terms correspond to paths, paths correspond to intermediate variables. Effectively then, terms correspond to intermediate variables. Right? And so every, let's see here, for every, I can't use that color, I've already used that color. For every intermediate variable, there is a corresponding term. Notice that the pattern, right, this little nonsense pattern that we noticed when we were talking about the faux cancellation, right, the highly illegal and nonsensical but tempting cancellation, yeah, that pattern does hold in remembering what these terms look like that correspond to a given intermediate variable. So, nice little hack. Look at your intermediate variables, correspondingly write down all your terms. Okay, so let's see this in action. By the way, why do we need this point of view? Why can't I just memorize the formula? Right? And the answer is when you have a composition of functions. Now, here I've set it up in a fairly natural and convenient way where the variables on the left are all called x sub something and the variables in the middle are all y sub something, etc. That's not how life works, right? The functions that you're going to be dealing with, I haven't the slightest idea what the variables are going to be called. It might not be x's, y's, and z's. It might be p's, q's, and r's. It might be a mishmash of different things. On the left, you might have k, l, q, and alpha. And in the middle, you might have z and beta and q, l. I don't know, right? Million different possibilities. And you can't memorize all possible versions of the formula, right? So what you need is a way to look at your scenario and interpret appropriately to your scenario what the formula should be. And I think this is a great way to do it. Okay. All right. So yeah, example. Here we go. Now in this case, I'll say conveniently set up the variables with the usual naming convention, right? But do notice that the numbers are now specific. We have 3 dimensions to 2 dimensions to 3 dimensions in our composition. And so what's the corresponding chain rule? Well, says here I'm interested in the partial of z2, there it is, with respect to x2, there it is. I have two different intermediate variables corresponding to the fact that there are two paths along which changes in x2 can contribute to changes in z2. And therefore I have two terms in my resulting chain rule. And just to color code things a little bit more explicitly, let's see here. This intermediate variable gives rise to that term. Notice that this pattern holds as to what's on the top and what's on the bottom, right? And then this intermediate variable gives rise to this term. Again, pattern holds as to what's on the top and what's on the bottom. So we just produced our own version of the coordinate multivariable chain rule just by looking at that diagram and identifying which variables are these intermediate variables. How are we doing? Is everybody on board? See the pattern? Okay. All right. Okay. Then a couple of partial derivatives, and you're all good to go. Just as a real quick partial of z2 with respect to y1. There's our formula for z2. Taking the partial, let me do it like this. Let's see here. There's our z2. Taking its partial derivative with respect to y1 gives me that. Okay. Yada yada for the rest of it. Okay, moving along. Now, here's another landmine, another thing to be on the watch for. Confusion of variables is a real problem. I'm going to come at this, as I often will, by starting with a single variable example. I think it's helpful to see these kinds of things in a single variable context first, right? So you can get your mind set around, okay, here's how to think about it, and then extending to the multivariable is, if you set it up right, same thing, right? I like to do that kind of stuff. So a single variable example. Here's a couple of functions, single variable functions, Calc 1 style functions. Nothing weird, nothing remarkable, right? Perfectly good functions. You're allowed to have a couple of functions, no big. Pretty reasonable question to ask is what happens if you want to take the derivative of the composition, and I claim that the mere asking of that question presents a problem that we haven't noticed yet. I'm going to leave that dangling. Something to think about. But let's talk about how we would compute the derivative of that composition, and I'm going to start by writing down a little bit fast and loose the single variable chain rule that the derivative of composition is the product of the derivatives, and just kind of being a little sloppy with my notation there. But look, these derivatives are pretty easy to compute, right? I mean, the derivative of g is that, and the derivative of f, right, is that. So isn't this product 6x cubed? And of course, no, it's not. That gets us a wrong answer. Because we were being fast and loose with the notation, a little too careless. Of course, when you use this Newton notation, it's the product of the derivatives, but the second function, its derivative has to apply to the first function, not to the first variable. Right, so again, Calc 1 long ago, and that being understood, well, g prime, looking at that function g, its derivative, g prime, is, it's the derivative of the cubing function is 3 times the squaring function. Sure. But what goes into that, again, is x squared, not x. Right, so again, I was with that first calculation that I have labeled wrong. That's what I did wrong. I didn't plug in correctly. And, okay, this does get us the right answer, sure, right? The thing we wanted to compute, we get the right answer, but I think that argument leaves a lot to be desired. We're taking this function of x, we're taking its derivative and then having to remember, well, yeah, you don't plug in x for x, you gotta plug in x squared for x, and it sounds almost contradictory, right? It's pretty unappealing at best, I think. Very unsatisfactory to me. So let me show you what I think is the overwhelmingly better way to do it, and that is to realize, as I already sort of suggested, from basically the start, as soon as I say I'm composing the functions, I've got to reconsider what variables I use to represent the functions. And let's just play it through. Right? I mean, if my first function is this, so f is written in terms of x, all right, so x is the variable that goes into the function f. What do you think would be a reasonable thing to call what comes out? Right? If x is the input, should the output also be called x? Ew, no, right, wrong, nonsense. The input is x. The output has to have a different name. Let's not call it x. That would be silly. We'll call the output, let's say, y. And remembering that we are composing. And when you compose, what comes out of the first function is supposed to be what goes into the second function. That as much as tells us that we need to rewrite, wrong color. We need to rewrite g using y as the dummy variable. You can't leave g written in terms of x. X isn't what's going in to g. Don't write it as if it is. Right? Does everybody see what I'm saying? Right? The total confusion of variables, if you leave, after you've established that you want to compose these functions, if you leave g written in terms of x, you are effectively using the name x to refer to both the input and the output from f. And that's outrageous. Okay. So all you got to do is rewrite the dummy variable. I emphasize, it's still the same function, right? I have not changed the g function at all. This function g, same exact function. G is the function that takes whatever you give me and it cubes it. Same function. Just writing it in terms of a different dummy variable. Okay, now having done that, how does that solve our problem? And, well, check it out. You can be as careless as you want now as you write down the chain rule. Derivative of a composition is the product of the derivatives. Again, totally sloppy in how we're writing it down. But let's see here. The derivative of f, 2x. The derivative of g, 3y squared. Naturally written in terms of y because we wrote g in terms of y. And we have effectively an immediate reminder that I've got to rewrite this in terms of x. And wait a minute, what is y? This input variable to g. Well, if it's the input variable to g, then it is also the output from f, so it's x squared. You plug that in, and again, we get the right answer. And I'm going to say we get the right answer in a way where we don't have to pull any nonsense and try to argue why x and x squared, or x squared plays the role of x, and oh gosh, what a nightmare of confusion. Right? This is just reasonable. Okay, so now all of that's Calc 1. Why am I telling you Calc 1 again? Well, because, again, it sets up an analogy, right? And this problem of confusion of variables, so much better dealt with by just rewriting the functions. Just don't do confusion of variables. You don't have to. Why would you choose to? Same thing applies in a multivariable context. So, again, here's a couple of multivariable functions. No problem. Perfectly decent multivariable functions. Fine. But the very moment that I decide that I want to compose them. Now I've got a problem. Same problem, so I'll be quick in referring to this, but if here's my composition of f and g, and if I'm going to write f in terms of x and y, like I have here, well, I don't want to call those outputs x and y. I want to call those outputs something different, let's say u and v, and again, as previously noted, what comes out of f needs to be what goes into g, and so I need to rewrite g in terms of my new, different dummy variables. And having set it up like this, having made this transition, having eliminated the confusion of variables problem, yeah, go ahead, take the derivatives. No need to remember to plug in a way that's unnatural and confusing. Here's the derivative of f. Here's the derivative of g. The derivative of the composition is the product of those derivatives. Don't forget, when you write them down as matrices, the one that's on the left in the diagram is first, and first, when you're talking about matrix multiplication, is actually on the right. I know that's counterintuitive in a way, but you got to keep that straight. And again, this is ultimately a consequence of notational choices that are too deeply ingrained in the culture, and we cannot change, right? It is what it is, so heads up. And then likewise, the derivative of g is second, and when you're talking matrix products, second is on the left. And then you multiply and plug in. By the way, let's talk through the plug-in a little bit. What am I going to do with this u right there, for example? Well, don't forget where it came from. U was the first input variable to g. That means that it's also the first output variable from f, which means it is x squared plus y squared, and you just plug in accordingly. How we doing? Everybody on board? Okay. Likewise for the v. By the way, I want to make an observation that applies to the last several examples I've done recently. Notice all the conclusions that I came to here came with the convenience of relying on this diagram showing the relationships between variables like this. And then likewise, the way I generated my chain rule here came from relying on the diagram to remind me of, wait a minute, which variables are where and depend on what and relate to which functions in which ways. Diagram helps us with that, right? And likewise here. Right? The diagram is what helps us to realize, wait a minute, I need to rename. What do I need to rename, and what would be reasonable choices? And wait a minute, what variable is that again? And it's right there in the diagram, right? So I urge you to rely heavily on the diagrams. I think they're extremely helpful, almost indispensable. So anyway, word of the wise. Okay, now that said, not every diagram is actually fair game. Let's not lose sight of this little reality, which is that what we are talking about, we can't get around this, right? The chain rule that we know, everything that we've done with the chain rule comes out of that matrix form, which specifically assumes that we're talking about let me write that a little bit differently, assumes that we're talking about a composition of multivariable functions. This is a very particularly structured thing. The outputs from the first have to be exactly the inputs to the second. Non-negotiable, right? That's what a composition is. That's the only example that we have in which we've got a chain rule. Okay, so yeah, sure, when you have where am I? When you have a composition, when you have a composition, that does produce a diagram, perhaps like so. But not every diagram necessarily comes from a composition of functions. And I think this is a pretty nice little simple example. You look at that and you see, different variables depend on different other variables, and so you've got a little diagram of sorts. Can I just start playing chain rule games with this? No, I can't. That doesn't come from a composition of functions. Give it a try. I mean, what claim would you make that actually is consistent with this diagram about which variables are functions of which other variables only, and which are then functions of which other variables only? You can't make it work. This is not from a composition of multivariable functions. So we don't have a chain rule for this scenario. Now that said, we don't have a chain rule, but this diagram can naturally arise out of a real world scenario. For example, this. Let's look at these equations down here. What's that? 4 equations there relating x's, y's, and z's. And you'll notice, for example, that each one of these equations, like let's look at this one, z1 depends on x1 and y1 and y2. Right? If you kind of map out a diagram representing this collection of equations, perfectly reasonable scenario that might come up in your engineering or whatever applications, you can end up with diagrams that aren't compositions. What do you do? And by the way, it's arguably a little worse than this. I'm going to point out that it's not even clear, for example, what a partial derivative even means here. If I were to ask, what is this? Partial of z1 with respect to x1, well, I mean, it's going to be tempting to feel like, okay, well, look, there's the output and those are the inputs. And it's tempting to say that this partial derivative represents that which you get from holding these constant and viewing x1 as your variable. But wait a minute. What do you mean? What are you talking about? You can't change x1 and somehow pretend that y1 and y2 aren't changing also, because they're functions of x1. So what does it even mean? Right? We got a nasty problem here. Right? Whew. Side note, let me tell you what people mean when they do write this, and here's, again, bad news, and don't blame the bearer. They mean 2 different things when they write this down. One thing that people can mean in some cases when they write this down is that we're going to view, wrong color. We're going to view z1 as being a function of these. We're going to forget about the fact, well, let's see, that doesn't work. We're going to forget about the fact that there's any reliance of the y's on x1, and then we're going to look exactly at that one dependence. That's one thing that people can mean in some cases when they write this down in this scenario. But they also sometimes, very often even in the same work, also mean look at all of the different paths along which changes in x1 can contribute to changes in z1. And those are clearly 2 different interpretations of the same thing, none of which really are uniquely right. Right? So this is a nasty scenario. So here's the good news. There's a really easy way to deal with stuff like this, and that is to just insert a new make-believe variable. And basically, I'm just going to insert a new variable like that. Notice that kind of partitions our variables into what you might call stages, kind of like what we have here, right? And all I got to do is just make sure that new variable is just the original x1 variable that it's kind of taken the place of. Okay, so sure, this new variable I'm going to call x1 star because it's just a placeholder to play the role of x1 in such a way that I can view this as a composition to avoid all these horrible, horrible confusions. Okay? And then just rewrite your equation accordingly. Right? And having done so, our diagram, that highly problematic diagram up there, just turns into this, where we totally have a composition. These variables are functions of those. These variables are functions of those. And no problem. And if you want to know the partial, you want to know the partial of z1 with respect to x1, cool. You've got three paths corresponding to three intermediate variables. That gives you three terms. No problem. By the way, don't fail to notice that partial right there, the partial of x1 star with respect to x. Well, x1 star is x, and so that partial is just 1. Everything goes through just fine. Right? So one little minor tweak doesn't actually fundamentally change the question, but it turns it into a problem that is susceptible to the tools that we actually have and avoids confusing nonsense. Okay. Oh, and let's see here. No, I have 3 minutes left. Okay. All right. So I think that's a nice trick. Be on the lookout for that. By the way, I wrote an exam question last semester, I think it was, where students had to implement this idea in the exam question. And so I think it'd be a really good exercise to go back at last semester, exam 1, I think it was. I think it's the very last question of that exam. Take a look at that. You might find that useful. Okay, so let's see here. How do you do second derivatives? We're not going to have time to get through this example, but I want to hit some highlights. This is I think best addressed by just kind of seeing it in action. And here is the big headlines of how to do second derivatives with the chain rule. First most important thing, rely on your diagram. Oh my gosh, so important. Can't emphasize this enough. Make sure to have a diagram like so that represents what you're looking at. So for example, z is a function of x and y, and r and theta being the usual polar coordinates tells us how x and y are functions of r and theta. And reminder, I like to think of coordinate systems as being functions. So literally, x and y are functions of r and theta, equations back in chapter 1, of course. So we're looking at a composition, and the diagram helps us keep track of how. So that's the first observation. Make an accurate diagram showing the relevant relationships. Next, second most important thing, don't move too fast. Slowly and carefully. Go slowly and carefully through the process and make sure to religiously follow the rules as to, wait a minute, what variable is playing what role in which part of the calculation, all informed by the diagram, and just carefully and obediently follow all of those constraints. Okay. All right, so let's see, how are we on time? Got a minute. So let's just do the very first part here. Let's, with all of this in mind, let's write down the r partial of z. So z, of course, is there. R, of course, is here. I have two intermediate variables corresponding to two paths, thus giving me two terms. Right? Now, I did that quickly, but make sure you can do that. Notice we have sort of an x term and a y term. And then some of these are actually pretty easy to compute. What's the partial of x with respect to r? Well, we have a formula for that. Explicit formula for x as a function of r and theta, and taking the r partial, no big deal. You can totally do that. And likewise, what's the partial of y with respect to r? Well, again, this is just straight up polar coordinates, and you can take that partial. You get sine theta. Notice that all I've done here is kind of choose an alternative notation, right? This subscript notation ends up being really convenient. And that's that first step, and we are out of time. So I'm gonna draw the line right here. We will pick up here on Monday. See y'all later. Have a good one.